But now we're cooling it by spraying water into the airstream. And this has the added benefit of not having so much dilution, not having to use a lot of dilution air, because when water evaporates, it absorbs a tremendous amount of heat, and that cools off, that removes the sensible heat from the airstream, and it goes into just converting water from a liquid to a vapor, but without increasing the temperature of that water during that step of vaporization. So we want to estimate the water addition rate needed in gallons per minute. Now there is a assumed knowledge that you'll know that we're talking about liquid gallons per minute when we're talking about a water addition rate. You don't add the water as a gas, so this is not a gaseous volume, this is a liquid volume. And the correct method here is using equation 824, again derivable from a mass balance. Here, m times C sub P times delta T for the gases must equal to m of the water times the delta heat of vaporization plus the C sub P for water vapor to go from the vaporization temperature up to the final temperature. Refer to chapter 8 for the derivation. But just using the equation straight on, we can get a certain mass flow rate of water, got a mass flow rate of air, plugging in a C sub P for water vapor, a C sub P for air, and a delta heat of vaporization. We get a mass flow rate of water. And then solving for that mass flow rate of water, we get 44 pounds a minute. The density of liquid water is 8.3 pounds per gallon, and therefore that gives us about 5.3 gallons per minute of water that needs to be consumed in the spray cooling system. Just as a point of interest, sometimes, depending on the final temperature you're trying to achieve in a water cooling device, you may need to recirculate water through the device. So you actually would pump in more water than that, or pump around more water than that into the chamber, but your net addition rate would be equal to the evaporation rate, 5.3 gallons per minute. Okay, I think I'm going to stop there for today. We'll come back and do this, finish up these problems on another day. Thanks very much for your attention. Hope this has been helpful. And of course, you won't see this big long break between when I'm recording. Hopefully, you'll just see the next minute's problem 23. Finishing up last time, we just finished up question 22 in the PE review questions. And so that brings us to question 23. Now, question 23 is simply another use of the ideal gas law. Here we have an airstream contaminated with 500 parts per million of benzene. And remember, that's always by volume or by moles, flowing at 2,000 cubic meters per minute at a certain temperature and pressure. And so we have all the information we need now to use the ideal gas law. We have a volume, a temperature, and a pressure, and a concentration of the contaminant. The process is operating 24 hours a day, and the process is carbon adsorption, which is going to control, or the control process is carbon adsorption to control these emissions of benzene. The working capacity of carbon, and that's the amount of the pollutant that can be adsorbed per gram of carbon in a system that's being regenerated. So this is each time it's reused. That's what the working capacity means. And it's typically, the working capacity is typically less than what you'd find in laboratory experiments where you saturate the brand new fresh carbon one time. So this is what you'd find, say, at a pilot plant or another operating system where you adsorb and desorb, then adsorb and desorb, and it's that difference after desorption what you can put back on the carbon. That's the working capacity. The working capacity is 0.2 of a gram per gram, and we want to estimate the carbon required in both beds of a two-bed adsorber unit if each bed is run for 3 hours and then regenerated while the other bed is online. And you're given the molecular weight. Okay, so the first step here in the solution will be to use the ideal gas law to get the mass flow rate of the benzene. So here we have the volumetric flow rate, Q, times the pressure, P, divided by RT. So that gives you the moles, right? Times the concentration of benzene, 500 over 10 to the 6th. So that's the partial volume now. When you multiply the total volume by the concentration, you've got partial volume, or another way of saying that is the volume of pure benzene. Now you apply that volume, 2,000 times this 510 to the 6th, times the pressure divided by RT, you got the moles of benzene, times the molecular weight, gives you the mass of benzene, and that'll be in units. Since this has liters, we've got to convert liters to cubic. This cubic meters and this liters haven't been converted yet, so we need to convert that. And so we have units of grams per minute, 3140 grams per minute. We're going to run this bed for 3 hours. The amount adsorbed is 565,000 grams of benzene, or 565 kilograms of benzene. So the amount of carbon required is 2826 kilograms of carbon, and that's in one bed. Since we have a two-bed system, we double that to get the total carbon. Okay. Question 24. I want the cross-sectional area of a carbon bed that's treating 20,000 CFM. The maximum acceptable velocity is 70 feet per minute. And that velocity is a superficial velocity. It's not the actual velocity of gas through the porous individual pores. And the superficial gas velocity, if you remember, is simply the gas volumetric flow rate divided by the total face area, so Q over A. Just like in a fabric filter, it's the filtering velocity. It's a superficial velocity because the different resistances in different parts of the bed here, or different parts of that filter, for example, you would have different actual velocities in different parts. This is an average, and it's an average as if the face area were unobstructed. So it's just taking the total volumetric flow rate by that face area. So we're going to determine the cross-sectional area of that carbon bed, and it's simply an application of what I just said, that since the superficial velocity, V, is equal to Q over A, turn that around, we'll get A is simply Q over V. So here we have volumetric flow rate, superficial velocity, 286 square feet. All right, so we move on to question 25. Again, dealing with carbon beds, chapter 12.